Today you are in chapter 5 where you will learn about complex function series and singularities. First, I remind you infinite series of real numbers because the definitions in complex are analogous. What is a sequence of real numbers? If f is a function from the set of natural numbers to any set of real numbers S, then f defines a sequence. We denote it by fn equal to an. For example, an equal to 2 power n. This is a sequence. Its members are 2, 2 square, etc. When do we say the sequence an converges to L, converges to a real number L? If given epsilon positive, there exists a positive integer m such that mod an minus L is less than epsilon for all n greater than m. Under this condition, the sequence an converges to the real number L. If an is any sequence, then summation an means a1 plus a2 plus a3 and so on. This is called infinite series. How do we decide the behavior of infinite series, convergence or divergence? We write Sn, the sequence of partial sums. Sn stands for the sum of first n terms. So if limit of Sn is finite, say capital L, then this series converges to capital L. And we write summation an is capital L. One more result from infinite series. When do we say this series is absolutely convergent? If summation mod an is convergent. If this is convergent, then we say that the sequence, this series is absolutely convergent. An absolutely convergent series implies the original series is convergent. So all these results you are familiar from the previous semester. Now let us see the complex sequence and series. So if f is any function from the set of natural numbers to a set S of complex numbers now, then this is a complex sequence. Zn is a complex sequence. Can write any example. 2 plus iota power n. This is a complex sequence. For each natural number, we have a complex number. When do we say the sequence Zn converges to some number z0, or you can use some other notation, converges to some number a, some complex number a? When do we say it? When given epsilon positive, there exists a positive integer m such that mod Zn minus a is less than epsilon for n greater than m. You see, the definition is similar. Furthermore, because Zn has real and imaginary parts, say Zn is xn plus iota yn, this converges to x0 plus iota y0, converges to x0 plus iota y0 if xn converges to x0 tends to x0, yn tends to y0. Means you can separate out the sequences of real part and imaginary part, and if these converge to x0, y0, then this sequence Zn converges to x0, y0. This can be proved, x0 plus iota y0. Likewise, what is infinite series in complex? If Zn is any sequence, then summation Zn, n varying from 1 to infinity, this is infinite series. Behavior of summation Zn is same as the behavior of the sequence of partial sums as you do in reals. Sn here is Z1 plus Z2 and so on up to Zn. Okay. Also, if these are real and imaginary parts, then you can separate out two series, summation xn plus iota summation yn. Okay, so if these two infinite series converge, this also converges. And if Sn tends to some number, say alpha, this series converges to alpha. If this converges to alpha 1, this converges to alpha 2, then this series converges to alpha 1 plus iota alpha 2. Okay, and this is of course equal to alpha. Similar is the concept of absolute convergence. This infinite series is absolutely convergent if summation mod Zn is convergent. And if the complex series is absolutely convergent, then it is convergent. It's easy to establish because xn is less than equal to mod Zn, right? Mod Zn is root xn square plus yn square. So xn is definitely less than equal to this. I can put mod also here. Now because this is convergent, this is less than equal to this, by comparison test you can say this is convergent. Likewise mod yn is less than equal to mod Zn, so this is also convergent, given that this is convergent. Okay, so hence absolute convergence implies convergence. So see this example where you can apply this result to see the behavior of the series. What is the behavior of this complex series? You can use the idea of absolute convergence. If you see separately, summation 1 plus iota over 2 whole power n. What is this? Now this is a real series and it is 1 by 4 plus modulus of the square root of 1 by 4 plus 1 by 4. What is that? 2 by 4 means 1 by root 2. 1 by root 2 whole power n. You know this is geometric series with common ratio 1 by root 2, that is less than 1, so it is convergent. This series is absolutely convergent, that means it is convergent. Okay. Next is power series. Hope you are familiar with power series in the real case. Similarly, we define power series in complex analysis. The series of the form an times z minus z0 whole power n. This is called power series in z minus z0. How to find the criteria for its convergence? Consider its absolute convergence. You know by ratio test, n plus 1th term over nth term gives you this. Limit of this should be less than 1 by ratio test. From this what do you find? Z minus Z0 is less than limit n tends to infinity mod an over n plus 1. Suppose this limit exists and is equal to capital R. So this series is absolutely convergent or simply convergent in the circle mod z minus z0 equal to R. This circle mod z minus z0 equal to R is called circle of convergence, and R is called radius of convergence. Okay, R is called radius of convergence. See this example. Summation z power n. If you compare with this one, what is an here? 1, z0 is 0. So if you find R, then R is simply 1 over 1 means 1. So what is circle of convergence for this power series? Mod z equal to 1. Mod z equal to 1. So this power series is convergent inside this circle. Alright. One more thing, if you are able to find the sum function of the power series, suppose it converges to fz, then this sum function is always analytic inside the circle of convergence. It is a very useful result. Fz is analytic inside the circle of convergence. So there is a connection of analytic function with the power series. You should know it. Fz, the sum function of the power series, is always analytic inside the circle of convergence. What is the sum function here? In this case, the sum function is 1 over 1 minus z. You can clearly see that its derivative is well defined. This is fz. So what is f prime z? 1 over 1 minus z whole square. You know this is well defined inside this circle. So it is differentiable everywhere inside this circle. That means it is analytic inside the circle of convergence. Alright, after this, let us see two very important series which are Taylor's and Lorenz series. First, let us see what is Taylor series. You are familiar with Taylor series in reals. It's similar to that. But statement of course differs. There you say that f is differentiable up to any order. Here we say f is analytic. F is analytic in mod z minus z naught less than r. In this open circle, the function is given analytic. Center z0, radius r. Then according to Taylor's theorem, at any z inside this circle, fz can be represented in the form of this power series given by summation n from 0 to infinity an z minus z0 power n, where n is given by nth derivative of f at z0 divided by n factorial. Here we don't need to say that f has derivatives up to any order, because there is a result. If function is analytic, then derivatives of all orders of f exist. Okay, so simply saying analytic, it's fine. So this is the result of Taylor's theorem. So what is the idea? That any function fz can be expressed in the form of power series given by this. Main thing is that this power series converges to fz inside the circle. Okay, see the example. Suppose you want to express e power z in powers of z, or you want to find its Taylor series about z equal to 0. What is that? What are its nth derivatives at 0? What is an in this case? Fn 0 over n factorial. You know derivatives, all derivatives of e power z are e power z, so you get 1 over n factorial. So what is this Taylor series? Summation n varying from 0 to infinity z power n, because z0 is 0, z0 we are choosing 0, over n factorial. So that the usual expansion of e power z. So using Taylor series you can find expansion of different functions in powers of z or in powers of z minus z0. Okay. Now let us see another important series which is called Lorenz series. This time f is analytic. F is analytic in this ring-shaped region or annular region. Means we have inner circle of radius r1, outer circle of radius r2. Function is analytic in this region. It is given. Then for any z inside this region, fz can be expressed as the sum of these two series. First is same as you are seeing in Taylor's, but second is different. Here n goes from 1 to infinity, bn times z minus z0 power minus n. An is given by factorial n over 2 pi iota integral along c fz over z minus z0 whole power n plus 1 dz, and bn is factorial n over 2 pi iota integral along c fz over z minus z0 power minus n plus 1. This is plus n plus n plus 1, and this is minus n plus 1. Here n goes from 1, 2 and so on. Here n starts from 0. Okay, so this is the result of Taylor's theorem. What is C here? It is a positively oriented contour encircling z0 inside this annular region. Positively oriented means counterclockwise orientation. Alright, so see the difference between these two results. Here the function is analytic in this annular region centered at z0. Here the function is analytic in the whole region. What happens if this function is analytic inside the whole region of the circle of radius r2? In this circle, suppose the function is analytic instead of annular region in the whole region, then you will see that this bn turns out 0. Why? Because fz times z minus z0 whole power n minus 1 becomes analytic in this region if z0 is not a singularity. Okay, in that case all bn's are 0 and Lorenz series reduces to the Taylor series, because first part is nothing but the Taylor series. Okay, so let's see an example where we will express a function in Lorenz series. So you can say Lorenz series is generalization of Taylor series in this kind of multiply connected region. This is simply connected region, that is multiply connected region. So let us see this example now. Fz is given by 1 over z minus 1 into z minus 2. We need to express this function in Lorenz series in three different domains. First, mod z less than 1. So for doing this, let us express z in the form of partial fractions. I can write it 1 over z minus 2 minus 1 over z minus 1, right? Yes. So in this region, let us write a valid Lorenz series. If mod z is less than 1, mod z by 2 is less than 1 by 2, that is of course less than 1. Now see how do we express fz in the form of the series. I can write it minus 1 over 2, minus 2 I have taken out, into 1 over 1 minus z over 2, correct? This term, plus 1 over 1 minus z, this is fine. Why we have expressed in this format? Because mod z less than 1, mod z by 2 less than 1 means this series is absolutely convergent in this. Okay. So we can write the corresponding series, that is summation n from 0 to infinity z by 2 whole power n. And this also can write summation n from 0 to infinity z power n. Correct? Why this minus 1 over 2 is taken out? Because under this condition, this series is absolutely convergent, you know. It is, if you take modulus, then it is a GP with common ratio mod z by 2 that is less than 1. Likewise, this is absolutely convergent because mod z is less than 1. Okay, so this is how you can express this function in the form of Lorenz series. In this case, all powers of z are positive. There is no negative power of z. Okay, so it's fine. All bn's are 0 in this case. Second, if 1 is less than mod z less than 2, then how do we manipulate to write the series? If 1 is less than mod z less than 1, then 1 over mod z is less than 1 from this. Yes. And mod z over 2 is also less than 1. So now I can write this fz like this, because z by 2 is less than 1. So first I would write as it is, minus 1 by 2, 1 over 1 minus z over 2. But second part, I will take out z from here. Z or minus z. Let us take minus 1 over z. So that I have 1 minus 1 over z here. Because mod of 1 over z is less than 1. So that the series you write is absolutely convergent. So from this I can write summation z by 2 whole power n goes from 0 to infinity, minus 1 over z summation 1 over z whole power n. Okay, this time you have this part also, bn part, negative powers of z, because you're writing this series about z equal to 0. So z naught is 0 in this solution. Okay. What if mod z is greater than 2? Mod z greater than 2. Then 2 over mod z is certainly less than 1. And 1 over mod z is also less than 1. So this time how to write this fz. This part is fine because 1 over z is less than 1, but this time instead of taking this minus 2 out, what should I take out? Z. I should take out z from here. So 1 over z, what is left? 1 minus 2 over z. And here minus 1 over z, 1 over 1 minus 1 over z. Now we can write again the series summation n from 0 to infinity 2 over z whole power n plus, not plus, it's minus 1 over z summation 1 over z whole power n. This time in both the series you are seeing negative powers of z. Okay, so depending on the domain you can manipulate your function to write the Lorenz series. Similarly, you can practice more problems. Next, let us see different types of singularities. First, isolated singularity. Singularity, do you recall from the previous chapter? A function is said to have singularity at z0. A function fz has singularity at z0 if it fails to be analytic at z0, and in every neighborhood there is some point where it is analytic. Now what is isolated singularity? Z0 is said to be isolated singularity of fz if you can find a neighborhood of z0 in which there is no other singularity. Naturally, then it is isolated. For example, if I write fz equal to 1 over z minus 1 into z minus 3, it has two singularities, 1 and 3. Both are isolated. Why? Because 1 is here, 3 is here. So you can construct a neighborhood of this point 1 where fz has no other singularity than 1. Likewise, a neighborhood can be constructed around 3. So these are isolated singularities. Now consider this function 1 over sine pi over z. What are singularities of this function? Where sine pi over z vanishes, it can be multiple of n pi. From this, what do we get? 1 over n. Z equal to 1 over n. For all non-zero integers, it is a singularity, and 0 is of course a singularity. But 0 is not isolated. These are singularities, 0 is also singularity. But this 0 singularity is not isolated. Why? 0 is here. First singularity is 1, second 1 by 2, third 1 by 3. So if you construct a neighborhood around 0, it carries infinitely many singularities of this function because this goes to 0. It is a sequence that goes to 0. So in this case, 0 is not isolated. Alright. We will focus on isolated singularities. If z equal to z0 is isolated singularity, then there exists a neighborhood of z0 in which there is no other singularity. Let us consider this center as the point circle, and this is outside circle. Point circle and this outside circle, this kind of situation, multiply connected region. So in this multiply connected region, we can write its Lorenz series like this, where an is this, bn is this. Okay, this part of the Lorenz series is called regular part, and this is called principal part. The part carrying these an terms, an times z minus z0 power n. This whole series is called principal part, and this is regular part, and the second one is principal part. Now, depending on non-zero bns, we classify three kinds of isolated singularities. First one is removable. Removable singularity. What is removable singularity? If in the Lorenz series of fz all bn's are 0, bn is 0 for all n, then such a singularity is removable. See this example. Sin z over z. You can write series expansion of sin z and divide that by z. What do you get? Z minus z cube over 3 factorial plus and so on. From this we have 1 minus z square over 3 factorial and so on. So you see there is no term with negative power of z, means all bn's are 0. You have all terms in the series about z equal to 0 with positive powers of z only, correct? So in this case all bn's are 0. So the singularity z equal to 0, z equal to 0 is of course a singularity, is removable. It is called removable singularity. Second type is pole. If bn is 0 for all n greater than m, in this series expansion, if bn is 0 for all n greater than m, then z equal to z0 is called a pole of order m. Is called a pole of fz of order m. Okay, if m is 1, in that case it is called simple pole. Alright, for example, suppose I write 1 over z minus 1 whole square. What is singularity of this function z equal to 1? What is Lorenz series of this function? It is already in the form of Lorenz series. How? All an's are 0 because there is no positive power of z minus 1. And b1 is also 0 here. If you compare with this one, b2 is 1, second term is here, b3 etc. all are 0. So what is it? b2 is non-zero, after that all bn's are 0, so it is a pole of order 2. Here z equal to 1 is a pole of order 2. Correct? What if I keep it z minus 1 only? Then it is a simple pole. In this case b1 is 1 and all other bn's are 0. So you understand. What if I write like this? Square into z minus 2 whole power 5. This function has two singularities. One is 1, other is 2. 1 is a pole of order 2, 2 is a pole of order 5. If you express this function in the form of Lorenz series, you will understand it. Third type of singularity, third type of isolated singularity is essential singularity. Essential. What is essential singularity? If there are infinitely many bn's in this series, or you can say there are infinitely many terms in the principal part of Lorenz expansion, infinitely many, then z0 is essential singularity of fz. See this example. E power 1 over z square, z equal to 0 is clearly a singularity. If I write it in the the expanded form in the series form about z equal to 0, then what do I have? 1 plus 1 over z square plus 1 over 2 factorial 1 over z power 4 and so on. So in this case, a0 is 1, a0 is 1, okay. All other ans are 0, correct? After that b1 is 0 because 1 over z is missing. 1 over z square, this is carrying b2 means b2 1. b3 is again 0. So you understand that this part belongs to this one, and there are infinitely many bn's which are non-zero. So here z equal to 0 is essential singularity. So there are three types of isolated singularities: removable, pole, and essential. Okay. Next we have the concept of residue. What is residue? Very important. Residue of fz at the isolated singularity z0. That we denote by residue fz comma z0. This is defined as b1. When you write Lorenz series of fz about z0, then notice the coefficient b1 of 1 over z minus z0. That coefficient is called residue of fz at z0. b1 you can write in integral form also from this. It is 1 over 2 pi iota integral along c fz dz. Residue provides a way to solve this integral. This is interesting. This gives you 2 pi iota b1. So if you know b1, you can write the value of this integral. Okay, so this is called residue. Now you have three types of singularities: removable, pole, and essential. In case of removable, you know all bn's are 0. So b1 will be 0. So residue in case of removable singularity is always 0. No need to calculate anything. But in case of pole, if it is a pole of order m, if this is a pole of order m, then we can show that residue of fz at z0 is given by 1 over factorial m minus 1, m minus 1th derivative of z minus z0 power m fz. And this whole expression is to be calculated at which point z0. This formula is very important. This formula provides you the residue of fz at the pole z0 of order m. What does it mean? Multiply the function by z minus z0 power m, differentiate it m minus 1 times, and finally divide by factorial m minus 1 to get residue. This derivation is simple, given in the lecture notes, you can check there. Okay, third type of singularity is essential. In case of essential, you have no formula. You have to write the function in the form of Lorenz series and then see what is the coefficient of z minus z0. For example, in this case, in this particular example, z equal to 0 is essential singularity. So what is the residue in this case? You will see what is coefficient of 1 over z in the Lorenz expansion of this function. So you are seeing with 1 over z there is nothing, means 0. So what is residue in this case? 0. The residue is 0. Okay. So let us do a problem for finding residue at the poles. So for removable singularity, residue is 0 always. For essential singularity, write the Lorenz series expansion and then see the coefficient of 1 over z minus z0. For poles, we have formula that we can use directly. So see this example, fz equal to 1 over z minus 1 into z minus 3 whole square. What are the singularities of this function? Two singularities, 1 and 3. 1 is a simple pole, 3 is a pole of order 2. So what is residue of fz at 1 according to that formula? 1 over factorial m minus 1. It is simple pole of order 1 only. So 1 minus 1 factorial. M minus 1 at derivative means no derivative. Simply multiply this function by z minus 1. Multiply this function by z minus 1. So you get 1 over z minus 3 whole square and calculate this whole thing at z equal to 1. So what do you get? 1 over 4. Second singularity is 3. But it is a pole of order 2. So m minus 1 means 2 minus 1 factorial. First derivative d over dz of what? Multiply the whole function by z minus 3 whole square and then differentiate it with respect to z. Finally calculate it at z equal to 3. See what do you get? 1 minus 1 over z minus 1 whole square at z equal to 3. That means minus 1 over 4. So this is residue of fz at z equal to 3. So you see calculation of residues at the poles is simple. Just you need to know that formula. Next we have the Cauchy residue theorem, a very powerful theorem for solving contour integrals. Cauchy residue theorem. It says that if f is analytic within and on a positively oriented simple closed contour C, except some finite number of singular points inside C, then integral of fz along C is given by 2 pi iota into sum of residues at the singularities inside C. Sum of residues at the singularities inside C. If you want to prove it, proof is very simple. Construct circles around it. Very small circles, non-intersecting, because these are isolated, so you can draw such circles. Then this function is analytic in the region between C and these circles. So by Cauchy extension theorem, you can say that integral of fz along C is same as integral along C1 plus integral along C2. Okay, but integral of fz along C1 is given by, because the z1 is the only singularity, I am calling this circle C1, C2 and Cn, is the only singularity inside C1. So by residue formula it should be equal to 2 pi iota into residue of fz at z1. Likewise residue at z2, 2 pi iota into residue at z2 and so on. Finally 2 pi iota into residue of fz at zn. So it is sum of all residues multiplied by 2 pi iota. So proof is simple, as I said. But this result is very useful for solving contour integrals. Let us see one problem. Solve the integral of 1 over z minus 1 into z minus 3 whole square along this circle. So to apply Cauchy residue theorem, you need to notice that which singularities are inside this circle. This is a circle of radius 4. Singularities are 1 and 3. Both are lying inside this. It is a circle of radius. Both are lying inside this. What does it mean? This integral should be equal to 2 pi iota into residue of fz at 1 plus residue of fz at 3 by Cauchy residue theorem. Okay. In the previous example, for this function, you have already calculated residues. Z equal to 1 is simple pole. This is a pole of order 2. So at this, what did you find there in the previous example? At 1, the residue is 1 by 4. At 3, it is minus 1 by 4. So this way, you are able to solve this integral. Okay. Notice one more thing. Integral is 0. That doesn't mean the function is analytic inside the contour. If the function is analytic within on a simple closed contour, then integral is always 0. But integral 0 doesn't imply this. Okay. So this way you can apply Cauchy residue theorem. One more thing, what if this circle is mod z equal to 2? In this case, what is the answer of this integral? This circle of radius 2. This time the singularity 1 is inside this, 3 is outside this circle, isn't it? So you will not consider residue at 3 because in Cauchy theorem the singularities must be inside C. What is outside, it doesn't matter. So what is the answer in this case? This minus 1 by 4 is no more there. Your final answer is pi iota over 2. So be careful. You need to, for applying Cauchy residue theorem, you need to make a rough sketch of your given contour and locate your singularities. Calculate the residues only at the singularities which are inside C. Make a note of this point. One more concept that would be helpful in solving the integrals, the contour integrals. Suppose in this contour there are many singularities, say up to z100. It means you have to calculate residue of fz at 100 singularities. That is a troublesome task. That is not economical. So in that case, we can use a concept that involves the residue at infinity. Details are given in the lecture notes. Here I am telling the output. This integral can be solved by using this formula that involves the concept of residue at infinity. What is C? C is a contour outside which there is no singularity of fz. All singularities are inside this. Then you can use this formula for solving this integral. In this formula, you need to calculate residue only at 0 for this function. Means in your function, first replace z by 1 over z, multiply by 1 over z square. This is a new function now. For this function, calculate the residue at z equal to 0 and use this formula to write the answer of this integral. This is especially helpful when there are so many singularities inside C and there is no singularity outside C. Okay. Let us do a problem using this formula. Let us see how it is applied. Suppose you are given 5z minus 2 over z into z minus 1 dz. C is this contour mod z equal to 2. You see that 0 and 1 both are lying inside this. So one way is that you use Cauchy residue theorem 2 pi iota into residue at 0, residue at 1. But we will use this one. According to this, outside this circle there is no other singularity, so we can use this. According to this, what do we need to solve? 2 pi iota residue of which function? First, you replace everywhere z by 1 over z in this function. 5z, 5 into 1 over z minus 2 over 1 over z, 1 over z minus 1. Okay? Replace everywhere z by 1 over z and then multiply it by 1 over z square. Calculate residue of this whole function at 0. First simplify this function and see what do you get. You get 5 minus 2z over z into 1 minus z, because this is cancelled and z is also cancelled from the denominators. So what is residue of this function at z equal to 0? It's very simple. Multiply this function by z and then put z equal to 0. So what do you get? 5 only? Yes, 5. So finally it is 2 pi iota into 5, 10 pi iota. Okay, so this way you can use this formula. This is very effective, especially when there are many singularities inside C and there are no singularities outside C. Then you can always use this formula for solving the integral. Next, what is the connection between 0 and pole? What is 0? First we should understand. Z equal to Z0 is a 0 of fz of order m if fz can be written in this form where gz is analytic and gz0 is non-zero. Means if z minus z0 factor is repeating m times in the factorization of fz, then z0 is a 0 of order m. If I write 1 over fz, then what is it? This is also analytic everywhere except z0. But now z0 is a pole of order m, isn't it? So if z0 is a 0 of order m for fz, then for 1 over fz, it is a pole of order m. This is the connection. It's clear. If z equal to z0 is a simple pole of a function of the type pz over qz, then residue of fz at z0 can be obtained using this formula. If it is a rational function, polynomial or polynomial, not necessarily polynomial, it's a function of the form pz over qz, where z0 is a simple pole of this function, then residue can be obtained using this formula. Why and where is it useful? First, let us see why this formula, why we differentiate and put z0. You see, if z0 is a simple pole of this, then this function should be of the form z minus z0 into, say, some function rz, where rz naught is of course non-zero. Okay, so this is qz. So what is q prime z from this? Z minus z0 into r prime z plus rz. So clearly q prime z naught is same as because this becomes 0 at z0, it is rz0. Okay, it is rz0. Q prime z0 is same as rz0. So in simple pole, what do? We multiply this by z minus z0. This is cancelled and then we put z equal to z0. So mainly we are left with rz0, and rz0 is nothing but Q prime z0. That's how this formula. Now see where it works. Suppose you are given cos z over sin z. Clearly it has simple poles at z equal to n pi. So if you go with the usual formula for residue of this function at n pi, what do you write? You will write limit z tending to n pi cos z over sin z into z minus n pi. But you see, you are not able to cancel here. You are not seeing the factor z minus n pi. So you cannot solve it. So let us use this formula pz over pz0 over q prime z0. So pz0 is cos n pi, and q prime you differentiate it and then put n pi. Differentiation is again n pi, means cos z, so you are getting cos n pi, finally it is 1. Okay, so this kind of functions where factorization is not possible and it is simple pole, you can use this useful formula. Now let us see application of the residues, or you can say the Cauchy residue theorem, for solving some real integrals. Evaluation of real integrals using the residue theory. See this example, you will understand how it is applied. Suppose we are interested in finding this integral 0 to infinity x square minus 1 over x square plus 1 into x square plus 4. This is real integral from 0 to infinity. We need to find it using the Cauchy residue theorem. We can write it in this form also, 1 over 2, because it is even function. We can write it 1 over 2 minus infinity to infinity x square minus 1 over x square plus 1 into x square plus 4 dx. Okay, now see how we apply this, how we solve this further using the Cauchy residue theorem. Consider this function z square minus 1 over z square plus 1 into z square plus 4. Okay, this function is analytic everywhere except the singularities plus minus iota and plus minus 2 iota. Am I right? These are simple poles of this function. Yes. Now construct a semicircle above x-axis of radius capital R, large enough so that these singularities iota and 2 iota are inside this. Iota and plus 2 iota are inside it. If this is R, then on x-axis the value of x here is R, here it is minus R. Now consider this semicircle boundary. It is a simple closed contour from minus R to R, and then this curved boundary of semicircle, let us denote it by CR. Because function is analytic within and on this simple closed contour, and there are only two singularities inside this, so by Cauchy residue theorem What is integral of this function along this whole contour? C is my minus r to r, this interval union CR. So along C this should be equal to 2 pi iota into residue at iota plus residue at 2 iota, correct? Residue of fz at iota plus residue of fz at 2 iota. These we can calculate for this function, and we will find that calculation of whole this is pi by 2. This part you can do easily. Okay, already we have practiced problems regarding finding residues at the poles. But this doesn't serve my purpose. I need to solve this integral. This I have found. Fine. Now, C has two parts, minus r to r and CR. So I can write this integral in this form. Minus r to r, x square minus 1 over x square plus 1, x square plus 4 dx. I'm not using jet here because I'm on x-axis. Y is certainly 0 there. So I can write it plus along CR. Along CR I have z square minus 1 over z square plus 1 into z square plus 4 equal to pi by 2. So I have broken this contour integral in two parts. Up to this it is fine. Now focus on this integral in the limit r going to infinity. In the limit r going to infinity, let us take its modulus. Its modulus is less than equal to r square plus 1 over r square minus 1 into r square minus 4 into modulus of integral along CR dz. This I am sure this gives length of CR. This integral gives length of CR. So I can write it pi times r. Length of the semicircle is pi r. Why it is less than equal to this expression, that you can understand, because if I take modulus of z square minus 1, this is less than equal to mod z square plus 1, correct? So on this circle what is mod z? R. So I can write here r square plus 1. So this is fine, less than equal to. About denominator, if it is mod z square plus 1, then I can write greater than equal to mod z square minus 1. You know this inequality in complex. So on CR it is r square minus 1. Likewise, this is greater than equal to 1 over r square minus 4. So reciprocal would be less than equal to. So this is fine overall. But in the limit r going to infinity, this goes to 0. Am I right? Goes to 0 or not? Denominator r power 4 you can take out. Numerator r power 3. So 1 over r is left here, something finite into. So overall it goes to 0 as r tends to infinity. So in the limit r tends to infinity, what happens to this left hand side? In the limit r going to infinity, left hand side becomes minus infinity to infinity, x square minus 1, x square plus 1 into x square plus 4. First integral is fine in the limit r going to infinity. Second you have checked goes to 0. So you see you have solved this part. You have found the value of this integral. So what is the answer of original integral? Pi over 4. So see this whole procedure, how do we manipulate in the solution to get the required integral. So once you practice some more problems, you'll be comfortable. When go through the textbook, you will find more problems there. See one more type of integral. Suppose you are given I equal to 0 to 2 pi over, not over, 1 over 2 plus cos theta d theta. Let us solve this integral using the residue theory. So, if I want to apply Cauchy residue theorem here, I need to convert the integrand or this whole integral in terms of z. So you know on a unit circle mod z equal to 1, z is cos theta plus iota sin theta, 1 over z is cos theta minus iota sin theta. So if I add the two, I can write cos z in terms of z like this, correct? And I can find dz also from this. What is dz? Minus sin theta plus iota cos theta d theta. This can be written as iota square sin theta plus iota cos theta d theta. Iota you can take out, then you will see that cos theta plus iota sin theta, that is again z. So from this you are able to convert d theta in terms of z, that is dz over iota z. Iota z, yes. So in terms of z, what is this integral? Along unit circle, theta goes from 0 to 2 pi, so you can write unit circle here, 1 over 2 plus cos theta is 1 by 2 into z plus 1 over z. D theta is dz over iota z. Right. Now it is simply a function of z. You can find its singularities and then see which singularity lies inside this unit circle. At that singularity, find its residue and apply this formula. There may be one or more singularities, so find residue at those singularities and then take the sum. If there is only one singularity, then 2 pi iota into residue of fz at z0. Do this calculation yourself. I am writing the final answer for you. You should get 2 pi over root 3. Main thing that I wanted to explain is if you have this kind of integral where sine and cosine functions are involved, limit is from 0 to 2 pi, you can use this approach for applying Cauchy residue theorem. Okay, there may be a couple of more types of integrals, but you have got the approach of solving real integrals using the residue theory. So hope you enjoyed the whole lecture. Thank you.